Hi students, we are deriving expression for the speed of sound waves in air. Now just now we derived Newton's formula and we found that there is a 16% error in the numerical value of the velocity of sound in air. Now it is being corrected by Laplace. So this is Laplace's correction applied to Newton's formula. Okay. According to Laplace, the sound travels, sound waves travel through air under adiabatic condition, under adiabatic condition. But Newton assumed it as what? Isothermal condition, is it not? According to Isaac Newton, sound travels through air under what condition? Isothermal condition, by keeping the temperature as constant. But Laplace very clearly explains that the sound waves travel through air under adiabatic condition. What is meant by adiabatic condition? Heat neither flows from compressions to rarefaction or from rarefaction to the compression. You look at this picture. The air molecules are very tightly compressed in this region, namely compression, so that heat will be developed. But the neighboring region, you see that in the rarefaction region, the air molecules are relaxed, a little away from each other. So naturally there is a tendency for the decrease in temperature in the rarefaction. But these compressions and rarefactions will not remain permanently as compressions and rarefactions. The next moment, the compression region will become a rarefied region, and the rarefied region will become a compressed region. Understand? It's a very quick process. So adiabatic process we have studied. Adiabatic process is a very rapid process, sudden, quick process, is it not? Moreover, air is a very bad conductor of heat. Air is an insulator. Therefore, there can be no heat flow from the compression to the rarefaction, and hence the temperature cannot remain constant. This is why Laplace assumed that the sound travels through air under adiabatic condition. Okay students, what is the equation of a state relating pressure and volume for an adiabatic process? The equation of state for adiabatic process is what? P into V raised to the power gamma is equal to a constant. For isothermal process, we wrote P into V is equal to constant. But for adiabatic process, it is P into V raised to the power of gamma is equal to constant, where gamma is the ratio of Cp and Cv. And this is equal to 1.4 for air. Okay, so this is gamma is the ratio of the principal specific heat capacities. Okay. So here P is a variable, V is also a variable, temperature also is a variable here, it is not a constant. Okay, now I will take this equation P into V power gamma equal to constant. I am going to differentiate, I am going to differentiate this equation 1. Okay, when I differentiate on the left hand side of equation 1, there are two variables, UV method, So P is assumed to be constant, and now the second V power gamma is differentiated. So I will get gamma into V power gamma minus 1 into dV plus V power gamma is kept constant, and pressure is differentiated, it becomes dP, and right hand side is a constant, so differentiation of a constant is equal to what? 0. Understand? So P into gamma into V power gamma minus 1 into dV. This plus term is taken to the right hand side, so that it becomes minus V power gamma into dP. Okay, now this V power gamma minus 1 into dV I will take on the right hand side. So that left hand side is P into gamma is equal to minus of, okay, V power gamma into dP divided by V power gamma minus 1 into dV. So here you will see that the V power gamma minus 1, when it is coming up, it will become V power 1 minus gamma. So that this V power gamma and V power gamma get cancelled. So that this P into gamma is now equal to minus of this V power minus 1 comes as V power plus 1. So V into dP divided by dV. This P into gamma I am rewriting as gamma into P. So this is equal to minus of dP divided by, I am adjusting the term dV divided by V. Okay. But the right hand side numerator is a change in pressure, or it is equal to what? Force per unit area, that is equal to what? That is a bulk stress, and denominator is change in volume by original volume is called as what? A volume strain. Okay, this negative sign indicates that whenever the pressure increases, volume decreases, and vice versa. So the right hand side is minus dP by dV by V must be equal to what? Bulk modulus of elasticity, and hence gamma times P is equal to the bulk modulus of elasticity and under adiabatic conditions. So BA is now called as adiabatic bulk modulus. Okay, bulk modulus of elasticity of air. So in the general expression now we can take velocity, okay, velocity of sound in air, velocity of sound in air is given by V is equal to square root of bulk modulus of elasticity under adiabatic conditions divided by rho. This is for air. This is for air. So now I am going to substitute BA. The bulk adiabatic bulk modulus is equal to gamma times pressure P, is it not? So in place of this bulk modulus, I am going to substitute gamma times P by rho for air. So the velocity of sound in air is equal to square root of gamma into square root of P by rho. So P divided by rho for air. Okay. Now already we have determined the value of square root of P by rho in the Newton's formula, and its value is found to be how much? 280. Is it not? And this value of gamma is found to be what? 1.4. So square root of 1.4 into 280. How this value came is from Newton's formula. Is it not? P equal to h rho g divided by density of air 1.293 we substituted, is it not? So that value is substituted here. So if you find the square root of 1.4 and multiply with the 280 means this is nearly equal to 331.3 meters per second. So what is the experimental value for the velocity of sound in air? This is equal to 332 meters per second. Is it not? So now Laplace's value of velocity of sound is nearly equal to the experimental value. This is 331.3, this is 332. It is in close agreement with the experimental value. And hence Laplace's formula for the velocity of sound in gases only is the correct one. Understand? So, my dear students, how to derive this expression? We started with the assumption of Laplace that sound travels through air under adiabatic condition, and the equation of state for adiabatic condition is P into V power gamma equal to constant, where gamma is the ratio of the principal specific heat capacities, namely Cp and Cv, and then we differentiated on both sides. Okay, So we arrived at a relation gamma times the pressure P is equal to the bulk modulus of elasticity under adiabatic conditions, BA. By substituting that, we have found that the velocity of sound in air is at NTP, this is at NTP, is equal to 331.3, which is in close agreement with the experimental value, namely 332 meter per second. I hope you must have understood well. Fine.